Hey folks, welcome to the fifth video in this series on deep learning in MATLAB. So in the previous videos, we built a neural network from scratch using layers. So we use convolution layer, fully connected layer, and the other layers together to make a network. So the building blocks in that case were these layers that MATLAB already had. And also in one of the earlier videos, we saw how to load in a pre-trained network and work with it. So using layers is what you would typically do, and 95% of the use cases is covered just by using layers. But if you want to implement your own networks, your own layers, you need to start using DLArrays. And this is what I'm going towards, and I want to write my own network without writing any layers, just using something called DLArrays. And so today's topic is about DLArray. DLArray is basically um, just an array used for deep learning. It's the alternative to tensors in PyTorch and TensorFlow. So, but I'm getting ahead of myself. So before that, the way a deep learning network learns or a neural network learns is via gradient descent. So imagine this to be your loss landscape. So this axis is the loss, and you have these two parameters. So this is your loss landscape, and the goal of any training phase of a neural network is to find the minima, or where the loss is the least. So this is pretty easy in this case, but real world examples, your neural network would have millions of parameters. So it's a very high dimensional space, and finding minima is hard. So what you do is you perform gradient descent, where you start randomly with one point, calculate the gradient, which tells you where the loss is decreasing, and you take a tiny step in that direction. And then you keep on doing that till you reach a reasonable point. So this is how gradient descent works. Um, Mathematically, it's denoted like this, where this is one of your parameter. So it's updated in the following way. The parameter equals the parameter minus some small step, learning rate. Its value typically is 0.01 or 0.001 and so on. And then the derivative of that weight with respect to the loss function. So this tells you how the weight needs to be modified in each step. Now here's an issue. How do we compute this derivative? For we can always compute it analytically with pen and paper, but that's not always possible. For neural networks like convolution, where there are these activation layers which impose non-linearity, the computation, even the analytic expression is quite complicated. So it would be very hard to analytically compute derivatives. On top of that, there are millions of parameters in a typical neural network, and a for loop for computing derivatives would be quite cumbersome. So the way modern frameworks overcome this behavior or this issue is by using something called automatic differentiation. And the way that works is the frameworks, including MATLAB, keep track of what computations you are doing. And with this map of computations that you have done with a particular variable, it is keeping track of derivatives as well. So you don't need to calculate derivatives separately. Derivatives are automatically taken care of while you're performing the computation. And this is only possible if you use dlarray in MATLAB. For TensorFlow and PyTorch, you use tensors because they keep track of derivatives. But in MATLAB, we use dlarrays. DLArrays are just a fancy word for deep learning arrays, and for all purposes, they are just like regular arrays. The only difference is that they keep track of what the derivatives are in this computation chain. To keep track of these derivatives, let me introduce two more functions, dlfeval and dlgradient. Now, dlgradient is easy to explain. All it does, it tells you the gradient of y with respect to the different variables. So if I type dlgradient y comma x, it gives me dy by dx. So this is pretty simple to keep track of. The next thing is dlfeval. Now, when you use DLArrays, MATLAB does not automatically keep track of the derivatives. It will keep track of derivative only when you tell it to. And the way you tell MATLAB to keep track of derivatives is by using the deep learning functional evaluator. So this is the DLF eval. So let's look at its syntax. So DLF eval takes in a function handle. This is a function handle, and then the variables. So you have a function which has some arguments, and these are the arguments that will be passed into this function. So when you wrap your function in DLF eval, instead of just calling the function, that's when MATLAB keeps a track of the derivatives. So remember, whenever you need to keep a track of derivatives, you need to use DLF eval. So let me demonstrate this on a live script. So give me a moment to pull open my live script. Okay, great. So let's begin. So first, I have created this variable x, which is just a random number. So let's point something. Now let me make a DLArray out of it. So all I need to do is use the command DLArray. That's it. So any array that you have, you just wrap it around this command DLArray. It becomes a DLArray. It's as simple as that. So boom, DLX is now a 1x1 DLArray. Great. Now let's use this function DLFeval that I mentioned. So suppose I want to multiply x by 5. I can do that, x times 5. So now if I do this, I get, actually, let me include a section break. Right. So my x is this, x times 5 is this. It worked out. But like I said, sorry, it should be DLX. So now if I run it, yeah, it's a DLArray that's 0.7881. But as I said, this operation does not keep a track of the derivatives. So we need to use DLFeval. So let me rewrite this in the form of DL function evaluation. And since DL function evaluation always requires a function, I will use a function handle, an anonymous function handle in this case. And let me explain. So since the operation that we are doing is relatively small, and I don't want to write a whole function to do that, I can use anonymous functions. So anonymous functions work like this. This is the function handle symbol. It takes in a variable, and all it does is it multiplies the variable by 5, and that is the output. So this is my entire function written anonymously within this small bit. The second argument was the second bit over here is the argument that will be passed into this function. So DLX would be passed in place of in, and it will be multiplied by 5. So this is all this function does. So let me now evaluate it. Let me press Control Enter, and I get the same result because it just multiplied it by 5. So nothing fancy has been done yet. But now we will try to compute the derivative. So say I have a, and I do a times 5. Okay, and now if I take the derivative with respect to a of this quantity, what should I get? I should just get 5. And that's exactly what we will try to get. So let's define y to contain that. And again, to compute derivatives, always do the computations within DLFeval. Again, I will define my anonymous function, which takes in a variable. And this time, what it does, it will compute the gradient. And I do that by typing the DL gradient command. So I pass in my y, which is the input times 5, and then gradient with respect to what. And then that's my function. And this is the argument that will be passed into this function. So this whole thing is my anonymous function. What it does, it takes in an argument, finds the gradient of it multiplied to 5 with respect to itself, and what is passed in this is DLX. So this should output 5, right? So if I run it, boom, I get 5. So this worked as expected. Great, that's awesome. Now, till now, we have been working with anonymous functions, and anonymous functions are relatively harder to write when you have complicated computations going on. In a typical neural network, lots of complicated computations would be going on. So all your computations you want to write them separately in a separate function and then pass in that function in this dlf-eval. So let me demonstrate that here. So just give me one moment to pull up my notes. All right, so I will define a function, compute. What it does, it computes output and the gradient. So let me call this grad. And it takes in an input. Oh, why did I remove that? It's a function, not a fun. Good. So the output would be just the input times 5. This is the computation that we are doing. And the gradient would be the gradient of this output with respect to input. Now, this thing could be as complicated as you want it to be. Here I have taken a very simple example, but you can do all sorts of things. And this gradient can contain all sorts of parameters that they are present in your network. So right now I'm just using one parameter, but then it could be a matrix of parameters. And my x also could be a matrix. Right now it's just a single number, but it could be anything. That's the beauty of this DLARRAY business. Great. So now I have my function that takes in an input, multiplies it by 5, calculates the gradient, returns both the output and the gradient. So let me now run that. So let's see. Again, I don't care about the output. I only care about the gradient. So let me call it dy over dx. And then again, always use dlf-eval when you want to keep track of derivatives. I pass in my function handle and the input that is required. So I'm passing in my function handle. This is my function handle and the input that goes into this function handle. And then let me run it. And again, I get the output to be 5. Great. So what I have done is demonstrated 2 ways of doing this gradient computation. One is inline using anonymous function, and the other is using a separate function to carry out the computations. Now, I again want to stress out the fact that this function could be matrix multiplications, could be convolutions, could be activation functions, could be anything, and still DL gradient would keep track of your gradients. So what you're doing, you're just performing the computations, and with one command, you are also keeping track of all the gradients. So dlf-eval in conjunction with dl gradient gets you the gradients out. So this is how automatic differentiation works. And this only works with DLARRAYs because remember, they are the only things that keep track of gradients. So this would be all for this video, and I hope you found it useful. And from the next video, we will make use of DLARRAY to construct our own first neural network. All right, have a great day.